So just a little bit of a review of our operations with functions. Starting off with inverse functions here for number 1. If we know that f of x is 3x minus 7, then technically we'll rewrite that as y equals 3x minus 7. To find f inverse of x, we switch x and y, and then we solve it again for y. So x equals 3y minus 7. And now we're going to solve it for y. So we'll add 7. X plus 7 equals 3y. And we'll divide by 3. So x plus 7 over 3 equals y, or if I rewrite that, f inverse of x, which is what y is x plus 7 over 3. Or 1/3 of x plus 7 over 3, however you want to write it with the fractions in it. Any questions on that part, finding the inverse? Okay. Number 2, find f composite g of 4. So f composite g of 4, which we're going to start off with the 4, and we're going to put it in one of the function. Which function do we start with in this case? Do we start with f or do we start with g? The 4 goes into g, right? So g of 4 is 2 times 4 plus 5. We put the 4 in for x in function g. 2 times 4 is 8, plus 5 is 13. So g of 4 is 13. That goes into f of x. So we put 13 into f. So that's 3 times 13 minus 7. 3 times 13 is 39. Minus 7 is 32. So f composite g of 4 equals 32. Any questions there? Okay. Number 3. F composite g of x means we're just going to do a generic composite to come up with one formula for it. So x goes into f first. So f of x is just 3x minus 7. That then goes into g. So replace x in g of x with 3x minus 7. So 2 times x, that's going to become 2 times 3x minus 7, and then plus 5. 2 times 3x minus 7 is 6x minus 14 plus 5 equals 6x minus 9. So that is g of f, or g composite f of x, is 6x minus 9. That's the composite. Any questions there? Okay, finally, fg of x. Remember, that's technically f times g of x. All that's asking us to do is to take those two functions and multiply them together. 3x minus 7 times 2x plus 5, which is going to give us 6x squared. Was that minus 14 plus 15? So plus x minus 35. So f times g of x is equal to 6x squared plus x minus 35. Any questions on that? Or any questions on any of the homework from last week? Okay. Make sure you remember to do that quiz then today. Have that finished by the end of the day for week 14. Today then we get to start on one of my favorite topics because I've worked in electronics and it's a very heavily used topic in the field of electronics. The next 4 days are actually going to be all very closely related. Today we're going to talk about exponential functions. When we talk about exponentials, before we dive into the functions, we should talk a little bit about exponents and exponentials themselves. We've done a lot of work with radicals, which are the inverse of exponentials, breaking them down and renaming them. With a radical, we took something like the square root of 20. We split that into the square root of 4 times 5, where we could take the square root of 4, which is 2, and we just leave the 5 inside the root to get 2 root 5. That was one way of reducing that and rearranging it. We had things like the third root of x to the 6th. That third root was the same as having a power of 1/3. So we were able to combine the root with the index, or the power with the index of the root to get that that's x squared. And we even dealt with exponents that were fractions. X to the power of 3/5. That's the 5th root of x to the 3rd, or the 5th root of x, all to the 3rd power. We could rearrange things and break them down like that. Exponentials can be worked similar to that. If I have 4 to the power of 3, we can obviously calculate it out, and I'm going to trust at this point that you guys know how to use the power key on your calculator to calculate that. But sometimes there's going to be times where it's more beneficial to rewrite that as an exponent in a different number. Since 4 is equal to 2 squared, I can replace the 4 here with 2 squared. So instead of 4 to the power of 3, it is 2 squared to the power of 3. However, 2 times 3 is 6. That's 2 to the 6th power. I can go the other direction. 3 to the 10th power. I might say, well, I want to write this with a base of 9 instead of 3. Well, 9 is 3 squared. Well, so to convert 3 to the 10th into something to the power of 9, 3 to the 10th, I'm going to break that down into 3 squared to the power of 5, because 2 times 5 still equals 10. So 3 to the 10th is the same as saying 9 to the 5th, because 9 is 3 squared, and 3 to the 10th can be broken into 3 squared to the 5th power. (32 to the power of 2x). I could leave it just like that, or I can write 32 is 2 to the power of 5. So combining these, I replace 32 with 2 to the power of 5, all to the power of 2x. 2 to the 5th to the power of 2x. Well, 5 times 2x is 10x. That's 2 to the power of 10x. Or we might have 4 to the power of 3x minus 7. We can do the same thing. 4 is equal to 2 squared. So I'm going to replace the 4 with 2 squared. So that's 2 squared to the power of 3x minus 7, which of course, we would distribute that 2 through the 3x minus 7. That's 6x minus 14. In your notes, I want you to try this one. 27 to the power of 5x plus 1. I want you to express that as 3 to a power. So 27 is 3 to the power of 3. So that'd be 3 to the power of 3 to the power of 5x plus 1, which is 3 to the power of 15x plus 3. Any questions there? Okay, now let's take a look at a basic exponential function. An exponential function, a basic exponential function, takes the form f of x is equal to a to the power of x. Sometimes there's a constant in front of it, a constant times a to the power of x. But the simplest form is just a to the power of x. So let's do an example. Let's say that f of x equals 2 to the power of x. And let's graph that. So I can make this a little bit larger, make it easier to see. Now we're going to fall back to making a table for these, where I pick values for x and I calculate what y is. And we're going to take a range. We're going to do -3, -1, 0, 1, and 3. If x is -3, y is 2 to the power of -3, which is 0.125 or 1/8. So that gives us the ordered pair -3, 1/8. That's going to be like right here. If x is -1, y is 2 to the power of -1, calculates to be 0.5 or 1/2. So negative 1, 1/2, that's right there. If x is 0, what's 2 to the power of 0? Remember, anything to the power of 0 is 1. So that gives us the point 0, 1 right there. You should be able to distinguish a slight curve in that. It's not going to be a straight line. If x is 1, 2 to the power of 1 is 2. Good. Giving us 1, 2 right there. Definitely seeing a curve. If x is 3, 2 to the power of 3 is 8. So 3, 8 definitely goes a little steeper. So we have an exponential curve that looks something like that. This curve models what we call exponential growth. One thing you will notice, when x is 0, this value would always be 1. The only way that would change is if instead of f of x equals a to the power of x, f of x equals some constant times a to the power of x. Then whatever that value is at 0 is just going to be that constant, c. Well, if we have exponential growth, that means there has to be something called exponential decay. Think of decay as shrinkage, reducing. A classic formula for exponential decay would be f of x equals 1/2 to the power of x. If I were going to make a table here and graph these, let's go -3, -1, 0, 1, and 3 again for x. If x is -3, y is 2, or sorry, not 2, 1/2 to the power of -3. Well, if you do that on your calculator, 1/2 to the power of -3, you get 8. 1/2 to the power of -3 is 8. So we get that point -3, 8. If x is -1, 1/2 to the power of -1 comes out to be 2. So we've got -1, 2. If x is 0, 1/2 to the power of 0. Anything to the power of 0 is 1. If x is 1, 1/2 to the power of 1. Well, anything to the power of 1 is just itself, so that's 1/2. So 1, 1/2 is right there. If x is 3, 1/2 to the power of 3 is 0.125 or 1/8. So 3, 1/8 is right there. So we get that curve. Notice this curve here is just the reflection left to right, or about the y-axis, however you want to put it, of the curve we had up here. The reason those are reflections is because that first one, f of x equals 2 to the power of x. The second one, f of x equals 1/2 to the power of x. The value of a here, we had 2 and 1/2, are reciprocals. If those numbers are reciprocals, they are going to be reflections of mirror images of each other like that. Now another way we could have written this function, instead of saying f of x equals 1/2 to the power of x, we could have done this. F of x equals 2 to the power of negative x. Remember that negative exponent is a reciprocal. 2 to the power of negative 3 would be 2 to the power of positive 3, which is going to be 8, which is what we had. 2 to the power of negative 3 would be 1/8, which is what we had here. So that actually shows you the negative x and the positive x, that's going to be a reflection about our y-axis. Well, obviously they get a little bit more complicated than that. We can shift our axes, shift our origin just like we can in other graphs. If I have f of x equals 2 to the power of x minus 3 plus 1. Let me finish a little bit of the graph here. If you remember, our starting point on these exponential curves is this point right here, 0, 1. It's always 1 unit up from the origin. Same here, 0, 1. That was 1 unit up from the origin. That is that spot when x is equal 0. Well, when we have a shift like this is just like any of the other shifts we've looked at. What happens to x, we do the opposite of that. That is minus 3, so that means we go to plus 3. This plus 1 then shifts us up 1. So our origin is moving from 0, 0 to the point 3, 1. Remember, technically this would be y minus 1 equals 2 to the x minus 3. So it shifts the origin to 3, 1. So that means our starting point of our exponential curve is 1 unit up from that, because it's 1 unit up from the origin. This is 2 to the power of x, which means it's a curve that looks... I want to draw this in at 1 here as a horizontal line, just because our curve always approaches that horizontal line. I'm going to explain that in a second. So our curve is going to look something like that. Remember, this point here at 3, 1 is the point that normally would have been right here. So why did I draw in that light brown line, that tan line? Well, because that is something we've mentioned before called an asymptote. It's a line that our graph can approach but never equal. As we move off to the left here, that curve is going to get closer and closer to that line. In this case, it's y equals 1. It's never going to equal 1. I can get out to negative 200, it's going to get really close to 1, but it's never going to equal 1. Just like up here, no matter how large I get here for x, no matter how far I go in this direction, this is never going to equal 0. It's going to get smaller and smaller and smaller, but never quite equal 0. In this case, that x-axis is our asymptote. Y equals 0 is our asymptote. So I want you to sketch for me one half to the power of x plus 2 minus 2. So where does the origin of our graph shift to? Instead of being at 0, 0, it's going to shift to where? Perfect. -2, -2, right there. So I'm going to draw that in as an asymptote across there at y equals -2. So, of course, our graph goes in 1 unit above that, doesn't it? And, oops, it goes down to 0. Since this is 1/2, it is a decay. It's going to look something like that. Any questions? So as we look at this basic form here, f of x equals a to the power of x. If a equals 1, what is it going to be? What's 1 to the power of anything? If a equals 1, that's just a flat line at 1. If a is larger than 1, that's one of those growth curves. And if a is less than 1, let's come here. Then it, of course, is one of those decay curves. Now for this class, if I ever asked you to graph one, you're more than welcome to plot points. You don't necessarily have to do the shift of the origin. I just wanted to show you that it does work the same. These exponential functions have a lot of applications, and we're going to get to those applications in just a minute. But I want to look at solving equations with exponentials in them. In a little bit, in the next couple of days, we're going to explore the inverse of an exponential. Remember, when we solve an equation, if I had y equals 3x, the way we solved that was we divided by 3, right? In fact, it doesn't even have to be y equals 3x. It could have been a number, 21 equals 3x. We solved that by dividing by 3. We got 7 equals x. The reason we divided by 3 is when we looked at this equation, our variable x had been multiplied by 3. And the inverse of multiplying by 3 is dividing by 3. Well, in an exponential equation, y equals 3 to the power of x, we can't, we don't have that inverse defined yet. If it were y equals x to the power of 3, what would its inverse be? How would we solve that equation? To get y by itself, to get rid of the third power, we would use a third root. The inverse of a power is its root. Just like the inverse of multiplying was dividing. In the next couple of days, we're going to learn what the inverse of an exponential is. For right now, however, if we're going to work with an exponential equation, all we need to know is this. If b to the power of x is equal to b to the power of y, if we have exponentials that have the same base, then their powers must be equal. So if b to the x equals b to the y, x has to equal y. So if I give you a simple one like 7 to the power of 19 equals 7 to the power of 4x minus 1, each side is an exponential that has the same base. They both have a base of 7. So I can cancel out that base of 7 and just know that 19 has to equal 4x minus 1. Now again, in the next couple of days, hopefully we'll get to it tomorrow, we'll look at the mechanism that allows us to cancel out that base of 7. But we know those powers have to be equal. Solving that equation, then what are we going to do? Add 1, good. 20 equals 4x, and then? Divide by 4, yes. So 5 equals x. Let's test that back into this equation, make sure it's true. Does 7 to the power of 19 equal 7 to the power of 4 times 5 minus 1? Well, yeah, 4 times 5 minus 1 is 19. 7 to the power of 19 better equal 7 to the power of 19. In your notes, I'm going to have you try 11 to the power of 12 minus 3x equals 11 to the power of 6. Solve for x. So this is saying 12 minus 3x equals 6. If we subtract 12, negative 3x equals negative 6, and we divide by the negative 3. X equals 2. Well, they don't always stay that simple. You've learned by now that it always gets worse. Let's look at a generic exponential, like 5 to the power of 6 equals 18,625. And actually, I'm going to do this. Instead of 5 to the power of 6, I'm going to say 5 to the power of x equals 18,625. In order to be able to solve this, remember, I have to have it in a form where I have exponents on each side with the same base. On the left side, I have an exponent with a base of 5. I need to express the right side as an exponent in the base of 5. Can 18,625 be expressed as a power of 5? So 18,625, if you do some exploring on your calculator, is 5 to what power? Well, I kind of gave it away earlier. It's 5 to the power of 6. If you have to, you just try it in your calculator. 5 to the power of 6, 15,625. I did that wrong. I want to make that work out for us. Put 15,625 in there. So that's 5 to the power of 6. So that means we're going to rewrite this equation as 5 to the power of x equals 5 to the power of 6, which tells us simply that x equals 6. We might have 2 to the power of 2x minus 7 equals 128. Can we express 128 as a power of 2? Sure we can. 128 is 2 to what power? We'll do 2 to the power of 6. That's not it. 64 is too small. We keep going. 2 to the power of 7. That's it. 128. So 2 to the power of 7. So that's telling us we can write this 2 to the power of 2x minus 7 equals 2 to the power of 7. What does that give us then for an equation to solve? That's saying 2x minus 7 has to equal 7. If we have the same bases, we can eliminate the bases and use that as just a linear equation. What do we do to solve this? Add 7. 2x is 14, and then divide by 2. X equals 7. I'm going to give you guys one to try. Let's go 3 to the power of x plus 1 equals 729. See what you come up with there. So 729 can be written as 3 to what power? 3 to the power of 6. So that becomes 3 to the x plus 1 equals 3 to the 6, giving us x plus 1 equals 6. And of course from there all we do is subtract the 1. X equals 5. we might run into something like this. When we look at this, it looks very difficult to solve because 32 cannot be expressed as a power of 8. So what we're going to have to do here is we're going to have to change the bases in both sides. Remember we did examples earlier of taking something like this and breaking the 8 down. 8 can be expressed as 2 to the power of 3. So if I can put that in here where the 8 is, instead of 8 to the power of x, this is 2 to the third to the power of x, which is 2 to the power of 3x. (32), on the other hand, can be expressed as 2 to the power of 5. Now we have this set up as two exponents with the same bases. So if the two exponents have the same base, we can eliminate the base and set the powers equal to each other. So 3x has to equal 5. How do we solve that? We divide by 3. So x equals 5/3 or 1 2/3. So we might have 25 equals 5x minus 3, 25 to the power of 5x minus 3 equals 3,125. Give that a shot at breaking that down and solving. 25 can be broken down as 5 to the power of 2. So when I substitute that in there, that becomes 5 to the power of 10x minus 6. 3,125 is 5 to the power of 5. So that means 10x minus 6 has to equal 5. We solve that. We'll add our 6. 10x equals 11. And we divide by 10. To get x equals 1 1/10 or 1.1, however you want to write it. Any questions there? I'm going to have you try this one. This one you're going to have to rename both of them. 4 to the power of 3x minus 7 equals 32 to the power of 2x. I'll give you about a minute to try that. 4, of course, is going to be 2 to the power of 2. Raising that to the 3x minus 7, that'll be 2 to the 6x minus 14. 32, of course, is 2 to the power of 5. Raising that to the 2x, that's going to be 2 to the 10x. Which gives us, as we eliminate our base of our exponents, 6x minus 14 equals 10x. Now, before we start to solve this, we realize that x appears more than once in this equation. So we have to deal with that before we solve. It's on both sides. We have to get rid of it on one side. 6x is the smaller one. So we subtract 6x, giving us negative 14 equals 4x. Now we divide by 4. We will get that negative 3.5 equals x, or x equals negative 3.5. How many of you had that?
I would have had that if I would have gone 5 times 2x instead of 3x.
Gotcha.
Yeah, I would have had that.
Okay. So anyway, you guys get the picture that we can solve those exponential equations by giving them the same base. Let's look at some applications here. Probably the biggest application is going to be in compound interest. Compound interest is going to be an exponential growth problem because the balance should be getting larger. And it does take the form of f of x equals some starting amount, we'll call it a constant, c or k, depending on how we're going to use k, times a to a power of x, or t is often used here in place of x because we're dealing with time. How do we get the little factor a? Well, let's say that we have 6% annual interest. And we're just going to say annual interest means it's compounded annually. A is a growth factor. Remember, we start out with 100% at the beginning of the year. If we add 6% interest, we end the year with 106%. A is the decimal form of that. So A is 1.06. Now, even though that's really close to 1, it is slightly larger than 1. And to be growth, remember, we just have to be larger than 1. K is our starting balance, beginning balance. X is our number of years. So let's say that we invest $5,000 at 6% annual interest for 8 years. Our ending balance, f of x, f of 8 in this case because it's 8 years, we're going to start out with that starting amount, that beginning balance of 5,000 times A is 1.06 to the power of 8. Which gives us an ending balance of $7,969.24. Now, there are different compounding factors. I did this annual interest to make it simple. It can be compounded quarterly, compounded monthly. Those would change that formula slightly. Let's say tuition is now $160 per credit. If it increases 2.7% per year. Find the tuition amount in 2030. Well, before we can put this in the formula, there's two things we have to do. One is we have to find our A factor here. Remember, that is going to be our growth percentage plus 100%. That'll be 102.7% or 1.027. Next, we need to find our X or T, depending on how you're writing the equation. The time, we wanted to know 2030. It's currently 2019. That's 11 years. Of course, our beginning balance is going to be the 160. So that cost in 11 years is 160 times 1.027 to the power of 11. So $214.48. So $214.48 is the anticipated tuition per credit in 2030. Well, it's not always a growth rate. Sometimes there's shrinkage factor. Let's say that you have, let's talk about snowfall. Let's say we have snow outside, even if it stays below freezing. I don't know if you ever noticed, the snow piles tend to still shrink. They go through a process called sublimation. It varies depending on wind strength. It's actually the movement of the wind that causes it to shrink. It actually directly evaporates rather than having to thaw first. Well, let's say the snow shrinks 12% per day. How much would be left from a 15-inch drift after 1 week? Again, we need to define two things. Our time here, or X, T, however, 1 week is 7 days. Our A, that growth or decay factor, is a little bit trickier. Here, is this growth or decay? Decay, it's getting smaller. So instead of being 100 plus our percent, it's 100 minus that percent. So 100 minus 12 is 88%, or 0.88. So our formula here, the amount of snow left after 7 days, is the 15 times 0.88 to the power of 7. Giving us 6.13 inches would be left. What do you think? Not horrible? Okay. General formulas. Where R is a growth or decay rate. Remember the meaning of that word rate? It's a percent written as a decimal. So if it is a 2% growth rate, that means R is 0.02. And we're going to use capital A as a starting amount. And T is simply going to be the number of periods. In most cases, that'll be years. If that's an annual growth rate, T would be the number of years. If it's a monthly growth or decay rate, that would be the number of months, and so on. So the formula is y equals, or f of x equals, that initial amount if it's growth, that'll be times 1 plus r to the power of t. If it's decay, it'll be y equals that initial amount A times, you probably guessed it, 1 minus r to the power of t. So let's look at an example here. After the age of 40, people on average shrink 0.1% per year for height. What's that? People do tend to shrink after the age of 40 because of spinal compression and bone decay, but it's not quite that predictable. For a person who is 74 inches tall at 40, predict their height at 65. I'm going to give you a minute here, see what you come up with for the formula. Remember, decide whether it's growth or decay, and we'll see what you come up with. So our initial amount is 74 times 1, is it plus or minus? Minus, because this is decay, and 0.1% will be 0.001. Then that's going to be to the power of, from 40 to 65 is 25 years. So 74 times, parentheses, 1 minus 0.001, close parentheses, to the power of 25, we get 72.17 inches. Another application that you hear a lot about is something called a half-life. It used to be you heard half-life discussed with radioactivity. Like you're told that this nuclear waste, depleted uranium, or and more often than not now it's depleted plutonium that they use in our nuclear reactors, that it has like a 235-year half-life. What that means is it takes 235 years on average for half of that material to deplete. So what that means is if you start out with 1,000 kilograms of material, in 235 years, it's going to be down to 500 kilograms. Now, where a lot of people mistake is they think that, well, in another 235 years, or a total of 470 years, then it should be gone, right? No. That means it's down to 250 kilograms. Each 235-year period, it gets cut in half. The less there is there, the slower it decays and degrades. So this is a radioactive decay, or an exponential decay. The amount of material left is equal to the initial amount times 1/2. You could think of it as being a 50% decay every period, every half-life, to the power of the number of half-lives. Well, the number of half-lives is really simple. That's just the number of years divided by the half-life. We'll just use H for half-life instead of HL. So that formula becomes Y equals A times 1/2 to the power of T divided by H. So if the half-life of technetium is 46 days, which actually is true, by the way. Come on. There we go. How much of a 50 kilogram, mass will be left after 1 year? So, Y is going to be the amount left is equal to the starting amount of 50 times 1/2 to the power of, well, our half-life and our time has to be in the same units. So I can't have 1 year and 46 days. So I'm going to write the 1 year is 365 days over 46 days is my half-life. So in my calculator, I do have to use parentheses in my power. So 50 times, I'm going to put my 1/2 in parentheses here, 1 divided by 2, to the power of, in my power I'm going to put parentheses 365 divided by 46, and then close that parentheses. I get 0.204 kilograms. Because that's such a short half-life, after a year, that 50 kilogram mass is decayed to 0.2 of a kilogram. We had mentioned earlier that there's an alternative way to write these decay formulas, Instead of writing it as 1/2 to the power of t over h, I could write it as y equals that initial amount times 2 to the power of negative t divided by h. Let's show that if I enter it in the calculator that way, I get the same amount. 50 times 2 to the power of, in parentheses, I'm going to get negative 365 divided by 46 in close parentheses. You'll notice I still get 0.204. The reason being, of course, is that negative exponent here. I can split 2 to that power, 2 to the negative t over h. I can split it as 2 to the negative 1 to the power of t over h. And of course, we know that 2 to the negative 1 is the reciprocal, 1/2. So these exponentials are going to require you to change your thought. Very similar to working with the radicals, where you had to change your thought into breaking them down in combinations and rewriting them using the factoring and all that stuff. These exponentials require you to adjust your thought pattern a little bit. Very different from most of what we've done for the semester. So the homework that deals with what we've done here is going to be homework 15A. So I want you to take a look at those for tonight if you can. We have this homework plus 3 more left. We have 1 more quiz left. And then, of course, next Tuesday is scheduled to be a review for our final test coming up on Wednesday. Like I said, you're allowed up to 3 hours for that final test, so make sure you schedule accordingly. We will only have the hour and 15-minute class again, but you will be allowed to take up to 3 hours for it. Anybody have any questions?
Yeah, did you say that we can pick up that test from D a little bit earlier than our class time?
Yes, I will have it sent out on Tuesday next week, so anytime Wednesday morning you can start it.
Okay, awesome.
Any other questions? Make sure you remind me of that, though, next week, Ezra, so when I send it out, I'll make sure I list instructions that you can start anytime before class. Okay, you guys have a great day. We'll see you all tomorrow.